Yeah. All right. So now you should be able to see the notebook I'm using. Can you? Is everything fine? Can you see my screen?
At least I can.
Yeah, we can see your screen.
Yeah, good. So let me briefly recall what we did last time, because I think I will not have the time to go through it carefully one more time, because we did quite a lot. But what we did was explore the idea of partner Hamiltonians. That is, we had some Hamiltonian in a way of minus. We were studying one-dimensional problems. We were studying them last time, and we're continue to study them today. On a line, on a half line, on some interval, doesn't matter, but it's just one-dimensional. So it's in the form minus dx squared plus some potential, and what we will assume going forward is that the ground state is known to us. Like at least we can solve for the ground state. For everything, for all other energies, well, we'll see how that will come along. But let us assume that we know the ground state function. Also, we normalize the Hamiltonian for the ground state function for the ground state energy to be 0. So it's h acting on phi naught is 0. Then we notice that well, we can actually restore the potential from the ground state function as phi naught double prime over phi naught. And this is well defined everywhere, since phi naught has no nodes, no zeros. Yeah. And then a wonderful idea comes to mind. How about we try to factorize the Hamiltonian into a product of A dagger A? Some operators which are almost like creation and annihilation, but they don't work in the same way here yet. They will work. They work the same. They work this way when the potential is x squared, but we'll see what's their meaning in general. So once we decompose it, we see that this new function we introduce, which is w prime, is related to the original Hamiltonian by this relation w prime squared minus w double prime equal to v. Now this can be seen as an equation on w prime, which is the Riccati equation. Now here the law of conservation of difficulty kind of shows itself, because solving this Riccati equation is identical to solving the original equation for the ground state function. If you look at it closely, if you write it in the linear way for the second order differential equation. But we already assumed that we know the ground state wave function, so that's not a problem for us. We quickly find that the solution is actually w prime equal to minus phi naught prime over phi naught, or the the logarithmic derivative of phi naught. Great, but this form allows us to state that that if phi naught solves h, that it is equivalent to having phi naught destroyed by acting using A. So A acting on phi naught is 0. Great, but this equation is a first order one. It can be easily solved. So phi naught actually turns out to be some constant times the exponent of minus w. Notice the absence of prime here. And we see that for the phi naught to be a ground state wave function that is a bound state, W must have a particular asymptotics as it goes to minus or plus infinity. It's written here. If W does not have such asymptotics, for example, if W is equal to say what? Say x. If W is equal to x, then we don't. This results in W prime equal to constant, and as you can see, the potential turns out to be constant as well, and that's the free problem, and there are no bound states there. All right, the next idea was to form a partner Hamiltonian. That is a Hamiltonian which is formed by the same operators A and A dagger, but in a different order. So it's first A and then A dagger. Yeah, after some calculation, we get the potential here. We see that it's very similar to the previous one, but the only difference is a sign, this one. And we see that there's a very nice relation between eigenfunctions of H1 and eigenfunctions of H2. In particular, if phi n1 solves the differential equation, solves the problem for the first Hamiltonian H1 with energy En1, which is greater than 0. So it's not the ground state. That's very important to note. Then we can rewrite H1 using our A and A dagger. And after we multiply everything, after we act by A from the left, we see that on the one hand, we have just the energy times A acting on phi n. But on the other hand, if we consider the A dagger A construction, we can find H2 in it. So the result is that A acting on phi n1 is an eigenstate of H2 with the same energy En1. Well, the same can be said. The same can be done in the other direction. If phi n2 is an eigenstate of H2, then by acting with the so-called creation operator, we get an eigenfunction for H1 with the same energy again. Great. So then we talked about how the supersymmetric formulation helps in this problem. And by introducing a Grossman variable psi, which then in the future we should be promoted to a field, obviously, but here it's just one variable. We and stating the commutation and anti-commutation relations for the SUSY algebra for quantum mechanics, we see that such a realization, as written here, Q plus and Q minus, directly proportional to A and A dagger, gives us as a super commutator of Q plus and Q minus some H, which is actually a sum of H1 and H2, but times the projectors on the boson subspace and the fermion subspace. Well, that is very nice because we there's now a way to sort of couple these Hamiltonians, these partner Hamiltonians, into one object. That will, yeah, and we looked how it works, how the statements that we proved above work in this supersymmetric case. Well, that's the only, well, the main difference is that the some function, some wave function phi n is now a sum of boson and fermion monomials. Yeah, but more or less it works in the same way. Yeah, and now a very important picture to visualize. It's the states and their energies. So in the beginning, we assumed that we normalized H1 to have a zero energy ground state. So phi naught has energy zero here. And by acting well, when we act with A by A, we get zero. Now all the other states, well, all the other states except phi naught, all the other eigenstates of H1, they get transformed into wave functions for H2 when we act with A. And that goes both for bound states and unbound states as well. This is well, the proof is just the same. There's literally no difference. But that is also very important to note that unbound states transform in the same fashion. And acting with a dagger, we go back from H2 to H1. So the pictures looks like this. We can see that if phi naught exists, then H1 and H2 differ by just one energy level. All their energy levels coincide except for the 0, 1, since H1 has a 0 energy eigenstate and H2 doesn't. Right. So this is a classical picture that people visualize in different supersymmetric problems, as I understand. Okay, now, yeah, well, we got simple relations between the bound state wave functions, well, between functions in general, but then we saw how it applies to unbound unbound states. That is, we assumed that W prime had the asymptotics of it were to tend to constants. That is, it's some W prime minus and W prime plus. Excuse this notation. These are constants, not derivatives. It's just we keep the W, we keep the prime here, not to have it in the formula for the ground state. Now, and this allows us to write how the Jost functions look for the first problem with some unknown, yet unknown coefficients, are reflection and transmission coefficients, RE and TE, with index 1. But if we know the Jost solution for the first Hamiltonian, then the Jost solution for its partner Hamiltonian is acquired just by acting with A. And as you can see, the asymptotics are affected in a very simple way. They're just multiplied by some constants involving the momentum. And the result is that the new reflection and transmission coefficients, that is, the coefficients for the partner Hamiltonian, are just the original coefficients multiplied by some phase shift. And it always has this form of a polynomial of P. Well, here it's just a first degree polynomial of momenta and the values of W prime at plus or minus infinity. Yeah. Then we looked at some examples.
So I'm sorry. So let me ask. So So you have reflection and transmission in each sector separately, right?
Well, yeah, I guess.
Yes, and
what
you
do you
say
mean by that?
how in bosonic and fermionic sector.
Yeah, of course. If we rewrite it again in supersymmetric terms, we should have two separate functions, Re and T, for well, not actually separate. As you can see in the supersymmetric formulation, well, as you can see in general, the potential and the partner potential differ by this term W double prime, right? And when we consider the scattering problem, one-dimensional scattering problem, we assume that W prime tends to two different constants on infinity. That means W double prime goes to 0. So I should write it here, W double prime goes to 0. And that means that on infinity, there are no differences between the partner potentials. Right, so what does that mean? That means that momenta, denoted here P plus and P minus, the momenta on minus infinity and plus infinity of the almost free problem. They are the same for the partner Hamiltonians. That is, they're the same for bosons and fermions in supersymmetric terms. But in general, of course, this if we use supersymmetric formulation, then this can be denoted as reflection for bosons, and here reflection for transmission for bosons. And when we act with A, we get the reflection and transmission coefficients for the fermions. So this can be called the fermionic and TE fermionic. Yeah. So does this answer the question?
So it means that if you know reflections and transmission for bosons, you automatically know reflections and transmission for fermions.
Yeah.
In fermionic.
Yes, and vice versa. Of course, you can act with a dagger and go the other way.
Okay, thank you.
Yeah, an important thing to note is that since R is just multiplied by a constant, same with T, but R is quite important here, that if we have a so-called reflectionless potential, a potential that has this reflection coefficient equal to 0, then its partner potential will also be reflectionless. So that's very, very neat. Also, the fact that the coefficients are multiplied by a phase vector means that the relation between the moduli, what stems from the conservation of probability current, means that it's not altered in any way, since the absolute value of these phase vectors is it's just 1. All right. Does have any maybe somebody has some questions, or maybe some questions have developed over the week that has passed since we talked about this? Well, if not, then let's look at the 2 examples that we studied last time. One was with the with this potential W prime equal to the hypertangent of X times some constant L. And the partner Hamiltonians turned out to be very similar, actually. They turned out to be L squared in both cases, minus L times L plus 1 over the hypercosine of x squared in the case of H1. And in the case of H2, it's the same, but L is shifted by 1. So it's L times L minus 1. This is actually, this is not the case in general. In general, partner potentials might look very different from each other. They might have nothing in common. Well, on the surface, at least. And we know that they have almost everything in common. But they might result in two very different looking problems. But in this particular example, it turned out to be the same. And that's today we'll explore when that is the case and how it helps how it helps us to solve problems completely. How it helps us to find all the wave functions, not just the relations between them. All right, so we looked at the particular case L equals 2, and we saw that the potentials looked like just some smooth wells and with different depth. And we solved for the ground state in H1, and the solution turned out to be some constant over hypercosine of x squared. And we also, now this is knowledge that that we have here, because the potential in H2 is almost the same as in H1, but we also got what we denoted phi2, which is the ground state for H2. It has non-zero energy, but still it's the ground state for that particular Hamiltonian. And it turned out to be some constant over just hypercosine of x, not squared. Now, this is not the general case. In general, we do not know we do not know in advance the ground state of the partner Hamiltonian. So please realize this. This is not the general case. But here we know it just because the potentials are the same. And this allows us to find the partner state by acting with a dagger. And here we got it, and it turned to be, and that is the first excited and the only excited state for H1, and it's just hypertangent of x over hypercosine of x. Yeah. Great. So
let me ask: how do we know that action of a dagger creates a zero in the state?
Well, I'd say that in general we should well, in one dimension problems,
of course.
Yeah. Well, I don't think that we should think of it as something that we know in advance, that acting by a dagger will create a node, but rather that we know that in one-dimensional problems, each successive excited state has one more node than the previous, and just by this consideration, we see that by considering phi naught and the excited state, we see that the excited state must have one more node than the ground state. I'm not sure that we can at least easily demonstrate that.
Okay,
the action of a dagger,
maybe it's possible to show it from asymptotics. Okay.
Maybe I'm well, perhaps. Well, I guess the asymptotics will probably show that, well, for example, phi naught, say phi naught decays as decays exponentially, but the coefficients are positive, so it's like, and when we act, and the same for phi 2. Phi 2 acts, it decreases exponentially, and when we act with a dagger, when we see the asymptotic form of a dagger, we see that the signs that we multiply, they are different on different infinities. So one of the asymptotics changes. Is this, well, either the
Okay,
left
so
or
we
the right
have
one.
at least 1 0.
Yeah. So this, yeah, that's how we go from no nodes to one node, or from an even number of nodes to an odd number of nodes. But I don't think we can say that it strictly increases by one.
Okay, so it's I just want to say that it's kind of, so it's an analytic equation to show that the action of a dagger increases the number of nodes by one.
Mm-hmm. Yeah, but again, here is not this is not how we think about it. Here we just consider the energies, and we see that the energy of the state is the same for H2 and H1, but the partner states, and this energy is strictly higher than zero, greater than zero. That means it's an excited state.
Yes, I'm just making a remark that
right.
For me to understand what is going on, I would like to have some analytic proof, since everything is analytic in general case, that action by a dagger brings just one extra node. You see, to be completely satisfied.
Well, that's not something that I can give.
Of course,
right
you
now.
don't need to give answers to all questions. So consider this as a remark.
Right. So one more thing about this particular example is that if we consider that we found all the states in, say, H2, it is true. It's the only state. It's the only bound state in H2, but we don't know this in advance. But suppose that we have found it. That means that we have also found all the states in H1. Since they should all be
all the bound states.
All the bound states, of course. Yeah, they should be phi naught plus the partners of the states of H2. We have no other like state here with this kind of energy, and that is easily seen if we act with A without a dagger. We should get a state here, but there is no state here. There is no other state. That means acting with A should just give 0. 0 as a wave function. And we know that the only state annihilated by A is phi naught. So that's how we see that there are no extra states in for H1. The same goes the other way. If we solved the problem completely for H1, then we also know the solution for H2, and there are no other hidden eigenstates in H2. All right. So, and we also looked at an example with unbound states. That is, we just took the same superpotential W prime from the last example, and we set L equal to 1. And that is an interesting case because the potential well, this is how it looks like. The original, yeah, so the first Hamiltonian, H1, has the potential that is just minus 2 over hyper cosine squared, just as we saw last time. But the partner Hamiltonian is a free problem, just shifted by 1. And that is when this is very fortunate, since for the free problem we know all the scattering data. We know that the refraction coefficient is 0 and transmission coefficient is 1. This is a very simple example just to show how the formula work. And here we acted with a dagger to get the just function for V1 for the first Hamiltonian. And we found the reflection and transmission coefficients for the first Hamiltonian. And they turned out to be 0 for the reflection coefficient, just as I remarked earlier. A reflectionless problem resulted in a reflectionless partner problem. And the transmission coefficient was just IP minus 1 over IP plus 1, where P is the momentum. All right. So, yeah, it took us some time, but we've recalled what was a week ago. And now let's continue. Now the main topic, as was announced, would be shape-invariant potentials. Now this is just a generalization of the situation that we saw in the first and the second example. That is, when the partner potential looks just like the original potential, but with a different constant. So here we had some constant over hyper cosine squared, and in the partner Hamiltonian we had the same thing, just the constant was L times L minus 1 instead of L times L plus 1. Right? So let's see, well, why is it an important case? Well, assume that we know how to solve the original problem. So assume that we have such a property. So we have this V1 and V1 of x, and it's just some general potential with a parameter, let's call it L, just to match the examples from before. Then we have a partner potential, and it's formed in the following way. V1 is W prime squared minus W double prime, and V2 is defined as W prime squared plus W double prime. And let's assume that this V2 is given by its important part, non-constant part, is just the same, but with a different parameter. Say, let's have it L1 and L2. And also, well, let's have some constant shift, possibly, doesn't matter. Let's call it, I don't know, F of L2. So it's just
It's better to call it C to show
C,
such a constant.
Sure. Yeah, right. Let's call it C. So why is this case important? Well, let's well, if this is true for, I guess, should we put a dependence on L1 here? I don't think we should.
It's better to put it.
Well, let's put it, it's no big deal. But if we have such a relation for arbitrary L1 and L2, I just assume that we have such a relation that Vx L1 is Vx L2 plus C. Oh, so wait. That's not good notation. Sorry. What I want to say is right. So one moment.
By the way, Tim, we
Yeah.
should not forget about breaks. So.
Oh, right. It's already
So
reached
now I
type
am
one.
now I am a visitor. So I keep trace of time. So now we
All right,
have
we can make a
10
break
minutes
right.
to 12. So I think now it's just a proper time to make a 10 minutes break, as we always do.
Sure. Let's have a 10-minute break now, and we'll continue after the break.
Yes, and
Yeah.
due to the tradition, we switch off audio and video during the break to show that it's actually a break, not a discussion time.
Well,
Okay?
just yeah, we'll do that. But before we go, does anybody have any questions? This seems to be kind of it's not very complicated examples,
Yes,
right?
yes. We also have at least 5 minutes for questions before the break. I'm sorry, I forgot about it.
Well,
so maybe I have a question, but let me ask it at the very end.
Fine. So if there are no other questions, let's have a break. So let's continue, I guess.
Yes, let's continue.
Yeah, now here, these formulas should be corrected a little bit. It's not, because this is not what I mean. All right. So we have two potentials, and they're partners. Now, assume that there is a generalization. B1 of x is actually it depends on some constant L. Now, how this generalization is done, it may be different for each case. Maybe there's a potential of the form, I don't know, 1 over x squared plus 1, and here's, say, 1 over L plus 1. or maybe it's how we had it before, L times L plus 1 just over cosine squared. And so this L can enter in different ways, but assume there is some dependence on this parameter. And V2 can also be generalized to include this parameter L. Now, the shape invariancy condition is stated as follows. Now, what if this V1 with the constant, some constant L1 is actually the same as V2 with some other constant L2 up to an additive constant. So here we can put here dependence on L1 or L2, doesn't matter, because L1 and L2 are connected by some transformation. So we can say that L2 is some function of L1, which we assume is invertible, for example. Yeah, I guess we should just f is invertible. Right. In general, L1 and L2 can actually represent several parameters, so it can be a vector of parameters, but we shall focus on just one parameter case. So notice that it's precisely what we had last time. Last time, V1, I mean, last time in this example, if you look at V1 and not forget the constants, this is how it looks like. It turned out to be L squared minus L times L plus 1 over cosine squared of x. And V2 turned out to be L squared. Notice the constant is the same. Minus L times L minus 1 over cosine squared. And here this relation is upheld. Let's see. Let's put it in some kind of blue, just to mark that it's a particular case of a general formula. We have V1 of x L plus 1.
There should be a plus somewhere, right? No.
No, it's a well, so it's okay.
Okay.
It should be negative.
Okay, sorry.
The non-constant part should be negative, right? So in this particular case, we can see that V1 of, say, x and L is the same as V2 of x and L plus 1, because this is L squared minus L plus 1 over, and this is, well, I haven't finished this formula yet, so, and this is L plus 1 squared minus L plus 1 times L plus 1 minus 1, so it's just L, so it's the same constant. And we can see that the parts that depend on x are the same, which is the important part, but the constant is different, and we should fix that by subtracting L plus 1 squared and adding L squared. So this is precisely this C of L. So the correspondence is just in this formula 1 to 1. And this is all a particular case, just to demonstrate. All right, so I hope you see now how this, what this formula means and how it works. All right. What does this shape invariancy mean? What does it give us? Well, after we get the second Hamiltonian, the partner Hamiltonian H2, so from H1 we go to H2 by this some kind of partner transformation. Let us shift H2 by a constant and get some, let's say H2 with a tilde, such that the ground state of H2 with a tilde is 0 again. So here, let me write this as A dagger A. This is A dagger, and this is shifted. The H2 tilde is shifted, so that the ground state has a 0 energy. And when it has a 0 energy, then just like H1, it admits a very nice factorization. And we call it A tilde dagger A tilde. Notice that the order here, it's the opposite of what was for H2. The A's with the tilde, they enter just like A's do in H1. All right, but what can we do with this? Well, we can apply the same procedure of finding a partner Hamiltonian and go to, say, H3. Here, the notation is a bit out of a bit wacky, but no, I'll fix it in a moment. I'm just explaining the general idea that we can go to H3, which is formed by the same rule. We just take the same operators and put them in different order. Again, we get by what we discussed before. This has no 0 energy ground state. All its states are above 0, so we can again shift it, get some H3 tilde, and factorize it with something like that. And we can continue this indefinitely. Well, in general, maybe, well, yeah, we should, yeah. This just continues on and on and on, and well, perhaps at some point we'll reach some kind of a stable point, and nothing serious will change. Maybe just the constant. Every time we'll get a shift by a constant, and the overall shape will not change, but it doesn't matter now. The idea is that we can apply the procedure of finding a partner Hamiltonian many times. So, and guided by this idea, we now introduce a better notation. So let us so all these potentials are they split into pairs, and the potentials in a pair shall be called Hn with the index 1 and Hn with the index 2. So these are the Hamiltonians connected by a partner transformation. And the index n will show how many partner transformations we have done, or maybe how many.
So 1 and 2 seems to be like bosonic and fermionic.
Yes, this 1 and 2 are just bosonic and fermionic. We can adopt this notation if you like. I just want to keep closer to the review that you sent everybody, because well, that review is like 120 pages long, has
Okay, so it's better
nice
to use both
explanations, papers.
notations.
Yeah,
So in
sure.
review, they're called 1 and 2. However,
Mhm.
we secretly remember that these are bosonic and fermionic.
Right. So with this better notation, let's put it in red. We shall call these. This first one will be H1, 1. Then H2 is H1, 2. So sorry that the indexes kind of exchange places, but and this H2 tilde shall be called H2, 1 because the index 1 means that it's now the original in a pair of partner Hamiltonians. Although it's partners are usually thought of as equal, right? In friendships and relationships, but here they're not strictly equal. One has a ground state energy of 0 and one doesn't. So this H3 is obviously just H2, 2. H3 tilde is H3, 1, and so on. Here we'll get H3, 2. So this is how it goes. So we have this hierarchy of Hamiltonians. It's H1, H2, and the same for the partners, H1, 2, H2, 2. And each one has has its own potential, and the notation would be the same. So it's yeah. Now let's mix this idea with the above idea of a shape-invariant potential. Now let's say that this condition holds for arbitrary L1. So just as we had in this particular example, this relation holds for arbitrary L, and you can see that it actually does because we did the derivation here for arbitrary L. We didn't require it to be integer or even real for that case. We just did it, and we got this relation. So
of course, it's algebraic relation, so we can put everything.
So this very important shape-invariancy condition, it holds for arbitrary L1. Let's say. Then let's see what are the potentials in this hierarchy of Hamiltonians. We say that H11, it's minus dx squared plus, and we use the notation for the potentials that we have here. So sorry if it's a bit confusing, but should I put 1 in brackets? Yeah, let's do it just to make it VI should be the same as this is the same.
Okay, so it's the confusion in the literature notation. So in the review they use not the best notation.
Well, it's very well, yeah. This notation is not very fitted to. It's not very well. Doesn't work very well with this kind of notation. So whatever. Yeah. So let's say that it's V1 of X and L1. Then and H2. Oh, not H2, but H1, 2 is by the shape invariance condition. Well, not here we just write it's v2 of some x and L2. No, x and the same parameter. Sorry. 1, 1. It's the same parameter. But by the condition, we have that this is the same as v2 x and some L2 and a constant shift L1. Right. Now, let us go to, now we notice that H21 is just H12 shifted by some constant, as we, well, by definition. So let's say it's minus E 0, 0, 2 to reflect that it's the zero energy of, sorry, just so many indices when it's hard to keep track. Whatever. So what I mean here is the ground state energy of H12. So we subtract it, and now the ground state energy is 0. And this is just minus Vx squared plus V2 x L1 minus this shift. But we see that this shape invariancy condition can be applied the other way as well. If we invert f, the function f connecting L2 and L1, we can write it as follows. We can write it as minus dx squared here, and v1 of x and f minus 1 of L1 minus c of f minus 1 of L1. So this is just taking a step back using the shape invariancy condition. All right. Now H2 is the same but shifted. So it's just the same V1 just with a different parameter, one of, and let's say plus shift. But after we go to H22, we see that we can again apply the condition, the condition that the potential is shape invariant. Because in this pair, H21, H22, the same thing happens as happened in this pair or H11 and H12. Let me let me erase this because it's not very vital here. So H22 will, by the condition, be just this potential transformed according to this rule. And that is V2 of x f minus 1 of L1. It's just the same parameter as before, as in H21. Now there's also shift C, which is this same parameter f minus 1 L1. Yeah. And this shift that we have here, let me write it out explicitly. So this is minus this is minus C of f minus 1 L1 and minus E naught 1 2. And here we have the same shift again. So it's C minus 1 L1 minus E naught 1 2. All right, so these cancel. Should they? They should. But again, we want to write H22 using V1. And we can do this. We can do this as just as we did on the previous step. And we get V1 of X and F, well, minus 1 of F minus 1 of L, F inverse of F inverse of L1. Then this minus C of F inverse of F inverse of L1. Sorry for the brackets. And then the shift. Okay, so as you can see, we got the same structure as in the last step. I hope this not very beautiful calculation convinces you that the shape invariancy condition continues to hold through the whole hierarchy. The whole hierarchy of Hamiltonians, they have the same potential in principle, just with different constants and with different shifts. All right?
All right. Now you need to make some statement about.
Yeah. Now, what does this condition give us? Assume that we have such a hierarchy and we know these potentials. We'll turn to examples and what can be said in general, but assume that we know it. Then let us just draw a picture similar to the one that we had in the very first example. Actually, let us just consider this example again. Example where W prime of X is equal to L hypertangent of X. And you can see that this L is just the parameter that we'll be using. This produces H11 in our notation as minus, here we take L equal to 1. So it'll be plus 1 squared, which is L squared, minus L times L plus 1, so it's just 2 over cosine squared. Now H1, 2 is minus dx squared plus 1, and here it's L times L minus 1, so it's just 0. So that's all. Yeah, so this is what we this is how yeah, so
do you want to say that from this so what I can see that from this consideration it's possible to get the complete spectrum?
Well, we're coming to this. We'll see that here we reached the free problem in just one step. So let's see what if we start from H say L1, yeah, just a general case. Then we have this, then HL2 is the same, but with a shifted constant here, L times L minus 1 of cosine squared. And HL, now HL, well, let's see what parameter should be put here. It's very simple. Let's look at this problem of HL2. And notice that since we know that this has a zero energy wave function, it's the ground state has zero energy. What should be done with HL2 for it to get a zero energy as well? Well, we see that if we just replace this L squared by L minus 1 squared, we'll have the same problem as above, but with L replaced by L minus 1. And in general, this sort of potential minus some, let's call it M, will have a ground state energy of minus M squared. This is E naught. This is a general case. This can be, well, since we can find the, we can factorize it and we'll find the ground state, and it has the ground state and the energy of minus M squared. So this is what we used in the very first example when we considered H2. And we said that, well, actually, we know the ground state function. That was because the potential was the same, just with a shifted constant. So let's see. We need to subtract L2 and add L minus 1. So it's the HL2 minus L squared plus L minus 1 squared. And we see that if we want to, we see what happens with the parameter. The parameter should obviously now be called L minus 1, since this is minus dx squared plus L minus 1 squared minus L times L minus 1. And we can see that it's just the this potential, this Hamiltonian, with L replaced by L minus 1. Right?
Yes.
Okay, and we can continue this, and it is clearly you can see that at some point we will reach H naught, or let's say H1, 1 and H1, 2. And H1, 2, as we've seen before, is just the free problem and the free particle. And the free particle has no bound states. All right, so let's draw how it looks on a picture, because this is instrumental to understanding all of this. Without this picture, it's hard to see what's going on. All right, so let's draw all the potentials of these problems in one picture with the same and on the same level. Now this is some general level. Now let's start with HL1. It has a, let's draw the hierarchy of HL1, HL minus 1, 1, and HL minus 2, 1, and so on until we get H0, 1, which is the free problem. And here we'll have H1. Now, HL1, that's some well. HL minus 1, 1 is also well, but it's a bit shallower. HL minus 2 is even more shallow. And so it goes until in H naught 1, we have just a free problem, no potential. And in H1, 1, we just have a just very shallow well. That's how it looks. Right. So what do we know? What do we know? We know from the very beginning, you remember, we assumed that we can find at least the ground state in our potential. So let's just do this. We can find the ground state here. There's something like this. But we can also do that for every other Hamiltonian, since their potentials are, well, basically the same, just they differ by a constant. So let's do it here and here. And finally, we can do it here. And in the free problem, there are no bound states at all. All right. Now, what else do we know? We know that operators A and A dagger, they relate states of partner Hamiltonians, and we know that this HL minus 1, 1, it differs from HL2 by a constant shift. So I've drawn them on the same level, but strictly speaking, they should be a bit on a bit different. On the same level should be of between HL1 and HL2, but there's also a shift in HL minus 1, 1. But we should. But this shift doesn't mean much in what I'm about to say. So relationship between the states of HL2 and HL1 obviously transmits to the relationship between states of HL minus 1, 1 and HL1. So that means this state has a partner here, and we already know. We can guess how it looks, and this is connected in the other direction. Fine, but this can be said about every other pair. So the pair of HL minus 1, 1 and HL minus 2, 1. So we can get the state here, and we can go back as well if we want. But let us just focus on the leftwards direction. Yeah, and here if we draw H2, 1. We can go this way as well. All right, but now we know more states, and we can again apply this procedure of acting with a dagger. And we can find a partner state for this state in HL1. So we'll get some function with 2 nodes, something that probably looks like this. But here we should be very careful, because these A daggers are actually not the same. You remember that A dagger is minus dx plus w prime. But now w depends on L, so A's also depend on L. So now this is promoted to AL dagger equal to minus dx plus, well, in this particular case, L hypertangent x. And similarly, a L without a dagger is just dx plus L hypertangent x. And we should be careful because these A's are different. Let's look. HL1 is AL dagger. This is AL minus 1 dagger, AL minus 1, and so on. Yeah, so in fact, what if we look at how we need to act, we say that this is actually up to a shift. It's AL dagger plus shift, right? Because it's just HL2 up to a shift. And we see that to get a state of this, an eigenstate of this Hamiltonian, we need to act from the left by AL dagger. Do you see it? Right. So this turns out to be these two and all of these that we will have above. They turn out to be exactly the same AL dagger, but the ones on the right, they're different because by the same consideration, this operator should be AL minus 1 dagger. And say this one should be a H2 dagger. All right. So, but now let's look at what we have. We applied it. We applied this procedure, but we can apply it more times. So to the left of H2, there's also an H3, and there we can find another state on this level. And then we can do the same for H4, and so on and so on. And that allows us to, when we reach HL minus 2 or HL minus 1, to actually get quite a few states. And in fact, these will be all the states in this problem. So
and new states would be the product of A daggers with different L's applied to the ground state of H1.
Precisely. Wow. So let's call the ground state of H1 B01. Then this state, for example, let's start with something simple. This state is A2 dagger by 1. And this state on the left, the highest energy state of HL, will be a procedural application of these A's, and it will be L dagger, AL minus 1 dagger, A2 dagger acting on phi-0 1.
And since A daggers are differential operators, that's great. So we know state in algebraic form.
Yes, since we know phi-0 1, and similarly we know, say, this one, this is phi-0 2, and we know all the states in this problem in the form of some product of operators A. So no, yeah, M minus K, and here we should probably have phi-0 m minus k minus 1. Let's see if it agrees with what we had in the very first example. Now we had H2. Now this was again in better. So this was H2 1, and this one was H2 2, but also H1 1 up to a shift. And we acted with a dagger, which was, as you can see, with a 2 here. So we acted with the A2 dagger. All right, so it's all, we made no mistake. Everything, the notation is in agreement with what we had before. All right, so all our states are in this form. Great. And A is just some known first order differential operator. And well, that's it. We solved the problem. We found all the states. Why these states are all the states and there are no extra states? Well, that's easy to see. Well, I already gave an argument like this before. If we have some extra states, say here, let's just act with A without a dagger. To go to the to go rightwards, and at some point we'll reach this situation where the energy of the state is clearly lower than the ground state of the corresponding Hamiltonian. But that is absurd. So that means that this function must be 0. But we know that the only function that is 0 after the action of A is the ground state of the previous Hamiltonian. So this actually goes to 0, and here we have a contradiction.
So here I have an immediate question.
Yeah.
We should not, so from this consideration, we can consider L being real. We will get exactly the same phenomenon.
Yes. This well, up to this H naught that I'm drawing here, I assume that it was the free problem, so it has no states. But
if it would have attractive potential, it would also have no states.
Right. Let's consider L not in. Well, here we can have it integer, or we can have it we can have it from just being a natural number. Then our hierarchy will look like this. We'll have some wells here, and then we'll have a well here, and the next one will have a well, let's say L equal to 1/2, right? So this is 1/2 times 1/2 plus 1, and the next one is clearly 1/2 times 1/2 minus 1. Well, and it's with a minus, so this is so if this is still a well, this turns out to be well, a hill. It's a how do we usually call it?
I would call it a bump.
A bump, yeah. That's a good name. So And obviously a bump has no bound states, and all the results are absolutely the same. We can still find an eigenstate here if it exists. In this particular example, it exists for any L such that it is a well and not a bump. But in general, it might not exist for even if the potential is negative. I don't know. I don't have a particular statement about that. But we find if we manage to find a ground state here, we can promote it to states of higher Hamiltonians in the hierarchy and solve the problem completely. And but notice that if before we acted with things like A3 dagger, A2 dagger, here we might have to act with A1/2 dagger, and then with A3/2 dagger. But that's no big deal. This L is just a parameter in A. In general, let me write it here. This is just W prime, and here let me put an index L. All right, yeah. So this works for general L as well, not just integer. Not yeah. Fine. And even though I used a particular example of the hypertangent superpotential, the picture is more or less the same for other possible superpotentials. What do I mean by possible? That means that the ones with right asymptotics and the ones that are shape invariant. Now, for completeness, it should be time to consider how the transmission reflection coefficients change, but I don't think it's very I think it's clear. We do the same thing again. Let me just comment briefly on this. T and R. No, it's actually important. Yeah. Let's use the same example.
Maybe we should not jam it, because after all, we are studying amplitudes. So bound states are important in studying amplitudes. So let me give an overall view why we are studying this. Not only because it's beautiful. It's because the goal is to study symmetries of amplitudes in supersymmetric quantum field theory. And in supersymmetric quantum field theory, okay, before we do it, we started with quantum mechanics to study amplitudes there. Okay? Now, supersymmetry in supersymmetric quantum field theory, supersymmetry in supersymmetric quantum mechanics leads to some kind of infinity relations that probably could be summed up to give some non-perturbative relations. Well, so we need to know something about amplitudes. And what is good, that in the case of quantum mechanics, in some cases, and we can write down the amplitudes. So in the solvable models, the amplitudes probably could be written down. And when we study amplitudes in the solvable models, we know that they should have poles where we have a bound state. So it's kind of important characteristic of the amplitudes. So that's why we need to know bound states, right?
Well, actually, there is even more importance in bound states when considering amplitudes, and I'll comment on that. So let me say why bound states are important for amplitudes. So
Okay.
how do we work with these transmission and reflection coefficients? Again, in principle, in the same way. If we know it for some problem, then we know it for all the next. So let me draw the same picture, and for integer L to start with. Let's start with integer L. That means we'll have some hole here, and it'll and it'll end at the free problem. Now, for the free problem, we know precisely that this R naught is equal to 0 and T naught is equal to 1, because it's the free problem. Then we act on some state. And here we know the wave function. Here on this level, it's just e to the I momento times x. Now we act with a dagger. Here, notice that this is index 0, this is index 1, this is 1, this is L. So here we actually act with a 1 dagger. And we get not an exponent, something different. And we also get the coefficients using the formulas that we got last time. Where are they? Well, the general formulas are here. So the transmission reflection coefficients, they are just multiplied by, say, the transmission coefficients is multiplied by I pi on the positive infinity plus this constant W plus prime, and this let me write it. Let me write it once, please. Let me write this R1 and T1. R1 is 0 because R naught is 0, and T1 is, as we said before, we use this formula, and P plus and P minus, the momentum on different infinities, they're the same, because the constant that our potential tends to, and it is actually 0, it's the same for both sides, and W prime plus and W prime minus is just the value of W prime on infinities, and since W prime is L times hypertangent of x, or in the case L equals 1, just the hypertangent of x, then its values at infinities are minus 1 and plus 1, and that gives I pi, sorry, I keep forgetting the plus. So it's plus 1. Here it's I pi minus 1 times 1, which is the T naught. Sorry, 1. All right, and then we go again and get R2 equal to 0 and T2 equal to, we multiply it by the same thing, but for the next operator A2. And this is nothing but IP plus 2, IP minus 2. And it's times T1, but T1 can be replaced by IP plus 1 over IP minus 1. And we can continue on and on and on until here we get RL equal to 0 and TL equal to a product of IP plus, let's say, plus M IP minus M. Why do you use M? Let me use K instead. And K goes from 1 to L. Great.
Great. But what if L is not
yeah.
integer?
What if L is not an integer? Then we do not have a free problem in our hierarchy, and that is bad news because we do not know the unbound state wave function for a general L. But here's how we can find it. I said that we have these kind of formulas, and they work for general L's, not only for integer ones. So, these formulas usually give some kind of probably some exponent, say e to the minus x squared times some polynomial, say Hermite's polynomial, or Legendre's, or whatever, some polynomial. And these operators, a dagger and a without a dagger, they just move from one polynomial to the other. But these polynomials that I'm talking about, they have a generalization to non-integer coefficients. No, not coefficients, but indices, which are given by usually by some integral formula or whatever. That means that if we recognize the appropriate polynomial, we know we have a closed form expression for the bound states. Now, if we have a closed form expression for the bound states, say by n L is some closed form.
But we already have a closed form for the bound state.
Well, it's not. We still have to apply the operators a dagger, and these are differential operators.
So what's the problem with applying?
Yeah, of course. If we apply it, we'll get something, but it's not very neat. We'll have to do it every time. To get each state, we need to do it many times. But if we notice some recursion relation for the polynomials in question, then we can write a general formula for a state, and it is usually expressed through some polynomial. But now we can do a very I don't know, bold thing. We can first recall that there was another solution of a similar form that we excluded, which was one with the wrong asymptotics, the one growing at plus or minus infinity. So
yes,
we add this phi n L, I don't know, tilde, that we excluded before from just out of physical considerations. And then we can take these two and more or less put n equal to some IP. This actually works, and if we use appropriate expressions for these bound states, this is just these expressions usually can be analytically continued to the complex plane, and putting n equal to some imaginary number is no big deal. That means we can get functions that are solutions to our Hamiltonian, but with these numbers n being instead purely imaginary. This actually works, yeah, and produces some, let's call it, I don't know, let's call it this sort of phi. This produces this phi p l, and getting from this phi p l to the Jost function is just a matter of well, here, strictly speaking, we get two, right? The pi pl and phi minus pl. And if we just take their appropriate linear combination, we get our Jost functions. Say the first and the second one. And these are just, the first one just gives, recall that it's, here it's E, here it's R, E, here it's T. So this can be done, and it has been actually done for a wide range of potentials. This way, one finds, the reflection and transmission coefficients, which are all part of an S matrix in quantum mechanics.
And do you know the formula?
For
do you
this,
remember the formula?
Yes, for this I have it, for the particular case.
Yes, for this particular case.
Yeah, for this particular case of L equal to minus x squared plus 1 minus L times L plus 1. For this particular case, let me give a brief comment. These considerations for general L's, not just integer, give us a relationship of this sort. RL and TL, let's say RL plus 1, TL plus 1. Are just phi p plus 1 over, or plus L plus 1. Sorry, let's have L here and L minus 1. AP plus L, AP minus L. And here it's, I guess it's a, it should be minus AP minus L. Yeah, like this. These are general formulas, and these can be seen as difference equations. Notice, difference equations, and they can be in general kind of solved, and the solution is consists of some gamma functions. However, the solutions to difference equations are always known up to a multiplicative constant that has a period of 1. Well, clearly, we have some solution for RL. Then if we multiply RL by, say, sine of pi L or cosine of pi L, we also get a solution that satisfies these equations.
And also sine squared. So
yeah, or sine squared, or any periodic function. And that is bad news because, well, again, if we know the free problem, if we have a free problem in our hierarchy, that's great. But if we don't, then we have no way of finding this periodic function, unless we use this procedure proposed below, with replacing n by some imaginary I times the momentum. And this actually allows us to reconstruct the transmission reflection coefficients completely, without any ambiguity. And the answer here, for example, is, well, for t, it actually coincides with what we can get from the difference equation without any periodic function, just keeping the absolute value of t less than 1. And it is, 1 second, I have it right. So it's gamma of L plus 1 minus EP, IP. Now it's, and here it's minus L minus IP over gamma of 1 minus IP, gamma of minus IP. And for RL, we have a similar thing. Actually, it's the exact same product of gammas. So I'll just put TL here. And here we have this periodic function that I just told you about. And it is actually yeah, it's I sine pi L over the hyperbolic sine of pi p. Yeah, so this is,
what about,
well, no, and you can see that it's 0 for integer L's, for L integer. And this is precisely the well-known fact that this potential is reflectionless for integer L's and is not reflectionless for other values of L.
So let me propose something. So my proposal is the following. So here we have this periodic function that you say we don't know. However, this periodic function could be uniquely determined by the perturbation theory.
In principle, yeah.
So it means that even if we don't know how to compute integrals, we can do it, and it is kind of instructive to do it on mathematics. So I mean, let us decompose T of L and R of L as a theory in L to get perturbative expansion.
Yeah, we can do that.
So derivative of gamma functions are known. So I would like to say that it's an alternative way to guess at this formula. Not only to guess the integral representation, but also to compare it, after all, but also to compare it with perturbative expansion. After all, our goal, I think, is to understand what is going on. Because we use, because in derivation of symmetries, we use perturbative expansion a lot.
Mm-hmm. Right.
So if you know the formula, you can just decompose. So what I think is good is that derivatives are known for both TL and RL. They are standard numbers.
Right. So it's already what? Almost 1:15
Yes.
here, so
Yes.
we're kind of out of time.
Yes.
Well, to be honest, there's still the topic of shape invariancy that we haven't gotten into, actually. Let's see.
But
The
you showed the
equation.
shape invariance in one particular case.
Yes, but yeah. Well, let me just say this. It turns out that almost all solvable one-dimensional problems have shape invariant potentials. What do I mean? What do I mean by them? But by it's this example that we studied a lot today with the constant over hypercosine squared of x. Then also it's the Coulomb potential can be written in this way. It's a bit surprising, but it can be done. That's a one-dimensional problem on a half line. Also, I don't know how useful this this listing that I'm giving here is, or trying to give. Perhaps I should just direct you to the review, because there's
That was
a very,
attached. That was
yes,
attached.
Yes, because there you can find a very neat. Oh, why don't I just show you? 1 second. Right. So this is. Oh, let me find the table I'm talking about. Here, this is this is a table of shape invariant potentials and the corresponding wave functions, actually in closed form, using Jacobi polynomials, Hermite and Laguerre polynomials. There's a similar table. I'm not sure if I guess it should be in this review as well, where the transmission and reflection coefficients are also written out. So that's great. So let's just look at the list of potentials, and we can see that the oscillator is here, something that we haven't talked about, but well, then there's a three-dimensional oscillator, Coulomb, Morse potential, the hyperbolic scarf 2, which is which is similar. This this is just 1 over cosine hyperbolic cosine squared, and also hypotangent over hypercosine, which can be thought of as what we consider extensively today, but also with different levels at different infinities. So it's it's asymmetric. Also this some trigonometric potentials. What it hides from sight here is that a few problems are actually limits or degenerate cases of these potentials. In particular, the infinite square well, that is basically a problem on an interval where we define the wave function to be 0 at the ends of the interval. These are our conditions. That is a particular case of this Eckert potential. No, not Eckert, sorry. 1 second. Of this Rosen-Morse 1, the last one on the list. If you choose alpha and a equal, then the first term goes away. No, sorry. What am I? No. If you choose b equal to 0, then there's only the first term left, which is 1 over sine squared, and the problem is on the interval from 0 to pi. But if you choose also a equal to alpha, then the first term also disappears, and we're left just with the constant. But that is a problem with the constant potential on an interval with 0 boundary conditions. And that is precisely the infinite square well. Also, one can find the step function in here as the limit of a hyperbolic tangent. The limit of a hyperbolic tangent is the sine function, the sine as in sine of a number. So that's the step function, and yeah, so almost all integrable problems are on this list. And that is quite remarkable.
So I'm surprised that elliptic problem is not here, but it's my personal surprise.
I should say that, well, you can read in the review that this list, we're not, well, these are shape-invariant potentials where the constants are related by shifts. So A1 and A2 in this table are just L1 and L2 in our notation. And as you can see, they all differ just by a shift. And that's just a particular case of the transformation of the constant.
I see.
So in this review, you can read about a transformation which is a scaling transformation, where L2 is some constant times L1, and probably it might happen that there are more complex rules for transformations that give rise to more integrable, and when I say integrable, I mean solvable here. And we can see that shape invariancy is practically equivalent to integrability. And perhaps with a more complex transformation, the elliptic problem will also find its place on this list.
Okay, but you see, I am not the person, at least I am not the person who is interested in finding beautiful solutions. Okay. So
but this is
my
just
personal
this is not just about beauty. If you look at the very last column, you can see the wave function in closed form. And here, if we will in these last examples, we use they use the Jacobi polynomials. If we use some integral formula for them, or just continue them to the complex plane along this parameter n, then this provides a way to find the scattering amplitudes for general for general constants, for general potentials.
Okay, so it actually, okay, I'm trying to see the scope of this.
Mm-hmm.
It may be interesting if we would study scattering amplitudes in integrable quantum field theories that are not given by perturbation theory. So probably in this case, we would like to look at exact S matrices. Okay. So thank you.
Mm-hmm. So
and
what do? We just leave this, or I mean, what about the shape invariancy condition? What do you think?
so I think
Should
it's
we
not good
meet again to
idea.
talk about it? Mm-hmm.
I think it's not a good idea to leave something in between. So let us separate our next meeting on Tuesday in two parts. So you would finish your talk, okay?
Yeah.
And I will start, and I will give some explanation on amplitudes and strings.
Mm-hmm. In truth, I don't have much to say. It's just
Yes, I
a couple of
understand.
important notes. Yeah, that
Yes,
I think are
but
important.
you see, I don't want to jam.
Right.
So,
Mm-hmm.
so next time, okay. So you will speak for say 20 minutes, and I will use the rest of the time. Okay. So if things could not be cut into exactly 2-hour pieces, they should be cut according to the logic of the explanation. Okay. So next time you will continue for some number of minutes, and as soon as you will finish, I will start explaining string theory amplitude. Okay. And then it will be our last meeting. So next Tuesday is 27th, next Sunday is 1st. So of course we will have no meeting. Now the question is about 3rd. So probably we should meet on 3rd or not. So it's the question how you are celebrating.
I have nothing against it.
Okay. So let us have the next meeting on 27th, then and then the meeting on 3rd. So I think that even if you drink a lot, you would be able to, even if you drink the 1st, 31st, and 1st, so it's possible to Okay. To come on third. Okay. So let's try to do it. Yes, drinking first, sleeping. Yes, third is, for me, third seems to be normal day. Okay. So that's it. Thank you.
Yeah, thank you for coming. Sorry for taking so long. It's already past. Oh.
So, Slava, are you here?
Yeah, I'm still here. Yeah.
So may I call you? May I go to your room just after this?
Okay.
Okay. Now, goodbye.
Okay, thank you.
Good.
Goodbye.
Thank you.
Bye.
Bye.
Yeah. Goodbye.